Recovery Processes by George Smith. When we stop exercising, we need to replace ATP and remove lactic acid, and this is known as oxygen debt. We continue taking in oxygen at a greater rate than at rest. EPOC is made up of fast or alactic acid components, which is responsible for resynthesizing ATP and phosphocreatine stores, resaturating myoglobin with oxygen, and the slow or lactacid component, which is responsible for removing lactic acid from skeletal muscles and blood, replenishing glycogen stores, and rebalancing the body's temperature. EPOC stands for excess post-exercise oxygen consumption, which is the additional oxygen the body consumes after exercise is over. When we stop exercising, we carry on taking in oxygen at a greater rate than at resting. The graph shows oxygen consumption before, during, and after steady-state exercise. The orange line shows oxygen consumption levels at rest, which are 4 milliliters. As exercise begins, the oxygen consumption rapidly increases from 4 milliliters up to 25 milliliters after 3 minutes, where it plateaus. After 10 minutes, the person stops exercising and the oxygen consumption levels immediately drop from 25 milliliters to 10 milliliters at 12 minutes. Finally, the oxygen consumption levels gradually decreases back to the resting levels of 4 milliliters at the 10th minute after exercise. It takes 10 minutes for our body to recover and go back to normal resting oxygen consumption levels. The fast components of recovery. The fast recovery components are also known as alactacid recovery, meaning without lactic acid. Alactic acid recovery can be used in both aerobic and anaerobic exercise, and is used to replenish our ATP and creatine phosphate stores, and hemoglobin and myoglobin stores in the first 3 minutes after exercise. It takes our ATP-PC system 30 seconds to be 50% replenished, 1 minute to be 75% replenished, and 3 minutes to be 100% recovered. They also need 3 to 4 liters of oxygen to be fully restored. For instance, this diagram could represent a swimming training session. If the swimmer did a 25-meter max effort sprint and then had 30 seconds rest before they needed to go again, then they would have half of their ATP-PC stores replenished for use in the next sprint. If they were expected to do 6 more sprints with the same amount of rest, then they wouldn't be able to replenish their ATP and PC stores as much compared to their first sprint. However, if they did a sprint and then had 3 minutes rest, then their ATP PC stores would be fully replenished and they could perform better. Myoglobin and hemoglobin stores get depleted during exercise and need to be replenished. Hemoglobin is in the blood and it carries oxygen to the muscles, and myoglobin is in the muscles and it combines with oxygen and takes it to the mitochondria to make energy ready for when exercise begins again. 0.5 liters of oxygen for 100% recovery are needed to replenish hemoglobin and myoglobin, and it takes 1 to 2 minutes. The myoglobin only binds to one oxygen molecule, but when the partial pressure is low, it binds quickly, so it is 80% saturated when the partial pressure is 20 hggm. The hemoglobin binds with 4 oxygen molecules, and this means that the partial pressure has to be higher, 70 hgmm. It is fully saturated in the lungs. When we exercise, we use up our glycogen stores, and we create waste products such as CO2 and lactic acid. During the lactic acid stage of recovery, in order to get rid of CO2 and lactic acid, and to replenish oxygen, both our ventilation and cardiac output remain above resting levels, EPOC. CO2 is found in the muscles, and it diffuses into the capillaries, where 70% is carried by carbonic acid, 23% by carbamine hemoglobin in the blood, and 3% by plasma in the blood. The blood carries the CO2 where it diffuses from the capillaries into the alveoli. The carbon dioxide is then breathed out. During a 200 metres butterfly, in order to cope with an increase in CO2 production, the swimmer's body increases the breathing rate so they can expire more carbon dioxide. During the slow component of EPOC, lactic acid is removed from the muscles and blood, 50% during the first 15 minutes after exercise and most of it after an hour. During recovery, when oxygen is present, some lactic acid that has built up during exercise can be turned into energy. 65% of lactic acid is converted into pyruvate, which is oxidized by the Krebs cycle. Eventually, the pyruvate is turned into CO2 and H2O. Lactic acid was thought of as bad for the body because it hinders performance and is painful to the athlete because it can cause cramp. However, it is actually used by the body to make energy. The other 35% of lactate is reoxidized in the liver and is turned into pyruvate. Then a process called gluconeogenesis converts the pyruvate into 5% glucose, which is stored in the liver, and 20% glycogen, which is stored in the muscle and liver. The remaining 10% of lactate is turned into urea, which can be expelled by sweat or urine. This is called the Cori cycle, turning lactate into energy for the body. Lactic acid can have a negative impact on sporting performance, causing fatigue and cramp. Our body has a buffering capacity to get rid of lactic acid. Hydrogen carbonate ions absorb lactate and form carbonic acid, which turns into CO2 and water, which are expelled by the lungs. Sodium bicarbonate, such as tonic water, is an alkalizing agent and it reduces acidity in the blood. By consuming it before a race, you can draw the lactic acid out of the muscles into the blood and it reduces the level of acidity in the muscle. When I was younger, I used to suffer from cramp at galas and I always used to drink tonic water. Now I make sure that I'm always well hydrated and so I don't get cramp anymore. I do still drink tonic water when I'm competing in a 1500 meter race. When exercising, our glycogen stores get depleted. The type of exercise affects how long the body will take to replenish its glycogen stores. For example, during intense and long activities, such as 800-meter running, glycogen can take up to 2 hours to recover. During very long periods of exercise, such as a 10K swim, the glycogen stores will deplete more and will take days to fully recover. As you can see in the graph, when the glycogen stores are very low, it will take them 48 hours to replenish. Active cooldown. There are also some other reasons why we need more oxygen after exercise. Our breathing rate and heart rate are elevated because we need to get rid of CO2. In order to do this, our cardiovascular and respiratory systems need more oxygen themselves. Our body temperature and metabolic rate is increased, and this also needs more oxygen. Finally, adrenaline and noradrenaline are released, and this increases oxygen consumption. Eventually, cardiac output, ventilation, and temperature will return to normal. The graph shows that after approximately 10 minutes of steady-state exercise, it takes 5 minutes for your heart rate and breathing rate to return to resting rates. When we exercise, the lowering of pH in the blood is sensed by pain receptors. During strenuous exercise, there can be damage to the muscle, but also connective tissues, which can be painful the next day. Muscle protein breakdown can cause inflammation and pain. In order to combat DOMS, it is much better to follow your main set of exercise with an active warm-down. For instance, after every training set of 1 hour at swimming, we always swim down at the end at a more gentle pace for 20 minutes. Ahmadi et al. 1996 found that active recovery immediately after the event encourages recovery and reduces muscle lactate levels faster than complete rest. The graph shows that athletes who did an active recovery after exercise had returned to their resting blood lactate concentration after 30 minutes, whereas athletes who had stopped exercising and then rested still had a raised level of lactate in their blood after 30 minutes. Suzuki et al. 2004 found that adding low-intensity exercise to the rest period after competition did not decrease an athlete's physical recovery and actually had positive effects on physiological recovery by improving relaxation. An active warm down keeps oxygenated blood flowing around the body, allowing its energy systems to replenish. The blood flow removes CO2 and lactate and flushes the capillaries with oxygenated blood. It prevents damage and pain in the muscles and reduces oxygen debt more quickly. It maintains elevated blood pressure, which helps the venous return to work well and preventing blood pooling. Other strategies for recovery. Eating well and keeping hydrated helps us to recover from exercise. You need to have eaten the right food before exercise so that your body can cope and is not exhausted when it is over. I try to eat a large bowl of porridge before I start a hard training set or a 1500-meter race because it supplies me with slow release energy. After my training, I eat straight away so that my glycogen stores can be fully replenished. Stretching and rolling are a really important strategy to prevent DOMS and muscle tightness. At the end of a training session, all the swimmers at my club stretch. For instance, we do the quadricep stretch where you grab your ankle and pull it towards your glutes in order to prevent tightness in the leg muscle and loss of flexibility. Occasionally, I have sports massage, which has the same effect as stretching and rolling, but it makes the muscles even more supple. Cryotherapy is the use of exposing your body to very cold temperatures in order to reduce inflammation created in the muscles from intense exercise. The Welsh rugby team used it in the lead up to the World Cup in 2011, and they said it allowed them to train harder and train for one extra day per week. Also, hydrotherapy is thought to aid post-exercise recovery because it pushes fluid from the extremities in the body, and this aids getting rid of lactic acid from your muscles. It gets rid of muscle inflammation and increases stroke volume. Wilcock et al. 2006.